Hey guys, Mr. Betts here. Now that we are ready to start trying to solve the tangent line problem, I want to talk about this idea of rate of change. This is something that you have done in pre-calculus classes. You've done problems where you find average rates of change. So, say for example, we have a car that's driving along a road. If we know how far that car travels and how long it took that car to travel that distance, we can take the distance divided by the time and we get an average speed over that time interval. Well, the tangent line problem is going to be kind of an analog, actually, exactly an analog to what's called an instantaneous rate of change. So rather than taking a time interval and looking at distance over that time divided by the time, we want to know how fast the car is traveling at any given time. And so we're going to need to have an understanding of what average rate of change and instantaneous rate of change mean and what those mean in the context of a problem. So I'm going to come back to these coordinate planes here in these graphs. But real quick, let's just refresh. These difference quotients from the previous video are giving us the slope of a secant line. So a slope of a line over some interval. So in the first one, the interval is going from the it's actually, I should go backwards here from the point at x equals a to the point at x. And the second one is going from the point at a to the point at a plus h. So these are both going to give us slopes, in particular slopes of secant lines. So if we look at some graphs with some context here, the slope of a secant line in any one of these coordinate planes actually has some meaning in terms of what the number is that we get for that slope. So for example, in the first graph here, we have x, which is a position measured in meters, graphed with respect to time, which is measured in seconds. Well, when we find the slope, we're finding a vertical change. So in this particular graph, a vertical change is going to be the change in the x value because that's the vertical units. And then we're going to divide by a horizontal change, which is going to be a change in time. So the slope in this coordinate plane is going to be a change in x divided by a change in t. Well, as far as units go, x is measured in meters and time is measured in seconds. So when we find a slope in this coordinate plane, we're getting units that are meters per second. So when we find the slope of a line through 2 points here, what we're finding is an average speed or an average velocity of an object in meters per second over that time interval. The same thing is going to be true whether we're finding a slope of a secant line like I am here, or if we were finding the slope of a tangent line. Slopes are going to be vertical units divided by horizontal units, so slopes in this coordinate plane are always going to be meters per second. If we go over to the second coordinate plane here, we have a cost in dollars for manufacturing a number of thingies. Thingies could be replaced with any sort of thing that you could manufacture. And a slope in this coordinate plane is going to be a vertical change, which is going to be a change in cost, which is measured in dollars, divided by a change in the number, which is a change in thingies. So the units that we're getting then are going to be dollars per thingy. And so what that tells us is how much it costs to manufacture each thingy over some time interval, or in this case, interval of number of thingies manufactured. The last coordinate plane, we have a population of bacteria graphed with respect to time. So units that we're going to get on a slope here will be vertical units, bacteria, divided by horizontal units, day. So a slope in this coordinate plane is going to tell us on average how fast the population is growing or shrinking in bacteria per day. So each one of these, in the context of a problem, the slopes have a particular meaning. And we get that meaning with an understanding of how we apply this difference quotient. So big idea for this is that a rate of change, how fast some quantity is changing, is going to correspond to a slope. And it doesn't matter if it's the slope of a secant line like we have in the first graph or a slope of a tangent line in the second graph. What matters is when we're finding slope, we have vertical change divided by horizontal change, which means that when we're dealing with units, we're going to have vertical units divided by horizontal units. Okay, so in the context of a secant line, this is going to be an average rate of change. In the context of a tangent line, we're going to have what's called an instantaneous rate of change. So the big idea here is that rate of change in the context of a problem and an application of calculus or slopes is going to be slope. It's going to be represented by slope in a coordinate plane. More specifically, an average rate of change is going to be the slope of a secant line. So average rate of change is a rate of change over some time interval. So remember, secant line is a line through 2 points. Instantaneous rate of change is going to be the slope of a tangent line. So it's going to be the rate of change of some quantity at the point of tangency for that tangent line. All right, so it's really important. This is like the biggest idea when we're dealing with the tangent line problem, is that rates of change, that's the same thing as slope. An average rate of change is slope of a secant line. Instantaneous rate of change is slope of a tangent line. It's like most important thing you're going to learn when we're talking about the tangent line problem.